Okay, they'll prepare it. Okay. Okay, welcome everyone to this first event of the EFCL Summer School. It's a great pleasure to be here, and even greater pleasure to introduce my PhD advisor, Yale Patt, who's here to deliver the first keynote. I don't believe Yale Patt requires any introduction to this audience, but maybe I'll mention a couple of quick things. Yale has been in the trenches for 60 years. I don't know, that's not up there yet, but he's going to talk about what he has learned over those 60 years. I will mention Yale has contributed a lot to how microprocessors are designed today. The seminal works he and his students have done in the 1980s, 90s, 2000s are essentially in all microprocessors that you have in your pocket, on your desk, on your laptop today. Essentially, he's invented the HPS paradigm, which is out-of-order execution of complex instructions with in-order retirement, which is the most important part that out-of-order execution works. And if you're interested, I'd recommend you take a look at his Micro 1985 papers, two papers that I believe have been cited very little, in my opinion, compared to the impact they've had. This is Micro 1985. They really describe how a microprocessor should operate in 1980s, and essentially this was materialized in Pentium Pro and later out-of-order execution processors. So that's research Yale has contributed. A lot of other things, including branch prediction, which I'm not going to talk about. Maybe he will talk about that. But I will mention Yale, more than anything else, he's a fabulous teacher. And that's the reason why I'm here today. Otherwise, you may not be seeing me today. You may be seeing Yale, but not me. I took his course in 1998 at the University of Michigan. And he wrote the book. At the time, he didn't have the book. He had the sheets that were printed. So we used to use those sheets to study. But I enjoyed the approach that he's taken to education. And that's the reason I wanted to go and study with him and work on computer architecture. And again, I would recommend to take a look at his book. He'll probably mention that today also. And I enjoyed spending many nights with Yale on teaching that course also, including into the wee hours of the morning, like 6 a.m., 7 a.m. So this is very early for Yale. I was actually worried that he may not show up to the keynote, but we made sure that worked. Okay, with that, I'm not going to mention Yale has all the awards. He's been a member of the National Academy of Engineering. He's received major IEEE awards and Benjamin Franklin Medal, mainly for his contributions. And also, he has received the ACM Karlstrom Education Award, which is one of the highest awards in ACM for education. With that, I think I'll leave it to Yale. And he'll be around the entire week. You can ask him questions.
We got the... good. So is this off?
What? Recorded, so you may want to actually use some mic.
The problem with, I want to use some mic. Okay, so maybe I'll have you stand next to me and hold this? No.
You could also wear it this.
Yeah, so the question is, can we, so I got to wear this, Salinas. So what do you want me to do with this? Put it on.
Just put it on your ear and then.
Put it on my ear.
Yeah, it just goes.
So what about this? This goes behind me, no?
Yes, yes.
We'll spend the first half hour getting me dressed, okay? No, so we'll try it, okay?
Yeah,
But the point is, yeah, okay.
It just goes like this. Okay.
No, the other way.
Ah, see? So the other way, good.
Let me do it. Does this look okay? Feel okay?
Do I feel okay? Of course not, but you knew that. The question is, can you hear me better with the mic? You can, okay. And you want this in my pocket? Okay.
or your belt? Yeah, sorry.
So we should have started this thing at 8 o'clock, see? Then maybe we'd be ready for it by now. Okay. So if they can hear me better, the problem is what I've discovered is that as the talk goes on and my voice tends to get louder, at some point it becomes unbearable for the people who are listening. And he called me his advisor. And for the first few years, I guess I was his advisor. But now for the last almost 20 years now, he's been my advisor. So, but I have some professors in the audience, and you know that role switches after you sign the dissertation. Okay, it's a pleasure to be here. I did ask Onur, I said, I need to figure out who I'm talking to. So are most of the people young people that are still in graduate school, or are they mostly senior faculty? And his answer was yes. And I said, are they mostly from academia or are they mostly from industry? And his answer was yes. It didn't matter. He doesn't understand A or B. Yes doesn't work. And so what I ended up doing is deciding that, look, there are going to be 4 brilliant tutorials over 9 lectures each. And so what can I do to add to that? And I said, well, why don't I just give you a few of the random thoughts that I've had as a result of being in the trenches now for, it's actually, what did I say? After 60 years, yeah. So I used to say almost 60. Now I can say more than 60. And so that's what I'm going to do today. And I don't know whether we can get through them all in an hour, but we'll see. So this is a list of them. And I'm not going to recite the list for you. The list will show up as we continue. What you see there is not the list. It's the start of the list. And that's the rest of the list. And we're going to end up with finally some advice as to what to do this week. And before that, the microprocessor of 2034. That's a lecture that I keep giving. And the only thing I have to do is just change the date to be 10 years after today. And things will be different 10 years from now, as we'll see. So those are the thoughts. So the first one, computer architecture was dead for about 30 years. And you will hear this nonsense from time to time from people who should know better. In fact, it's from people who never did anything during the last 30 years, except complain that there was nothing done in computer architecture the last 30 years. And of course, that's nonsense. In fact, branch prediction in the last 30 years. In fact, at the start of the last 30 years, there was no branch prediction. The only thing was Jim Smith's 2-bit count, saturating 2-bit counter, which gave you the wrong prediction 20% of the time, which meant that 20% of the time you had to throw everything away and start down the right path. That's changed. My branch predictor ended up 97% of the time being accurate. So the 20% of throwing things away changed to 3%. And if I thought that was always called Mr. Branch Predictor, another nonsense title. And that's changed, by the way. Today, Mr. Branch Predictor is Andrei Seznek from INRIA. You know, he took a job at Intel, and then he changed his mind. He's back now, no longer at Intel. He never left INRIA, by the way. You know, you do Zoom meetings, which I've never liked, but that's what he did for the last few years, working on a microarchitecture that boggles the mind with the issue with and everything else about it. But 30 years ago, the issue with was one instruction at a time, okay? And the mouse with a single micro-op per instruction. And the processing was done in order. Now everybody does out of order, everybody does complicated instructions, everybody does issue with, and the guys at Intel, I don't know whether it's public information yet now. So you don't have any NDA with Intel, right? You do or you don't? So, no, the reason I was asking is because I'd like to be able to tell them what that issue with that Intel is working at, except that if it's, privileged information, then I can't do it. As far as you know, it's privileged, then I won't do it. The point is, and that's just the beginning as you look through this whole list. Plenty of stuff has been done over the last 30 years. So when people tell you that the architecture has been dead for a long time, you can say, oh, you've been listening to Professor. No, I've agreed not to pick on him anymore, and so I'm not going to identify him. Research versus scholarship. That's an interesting thing that I discovered from being a professor at the university, where the other departments, and I don't care whether you're talking about science or archaeology or whatever, when they say research, what they mean is studying what has been to understand what's going on. I don't call that research, I call that scholarship. But in engineering, we don't give you any credit for that. You can study all you want, you can understand terrifically, but no credit unless you also come up with a widget that capitalizes on that understanding. And I think that's a serious mistake with our field. Because, so for example, he mentioned the out of order execution. So that was probably my biggest contribution, is being able to execute instructions out of order and do it correctly. Out of order was introduced by Thomas Sewell on the IBM 36091. The instructions were Mickey Mouse floating point, multiply, 1 micro-op. And when we did it, the instructions, some of them had 10, 15 micro-ops, making that one instruction in the ISA. We came up with a mechanism, my 3 students and I, Wen-Mei Hu, Mike Chevenow, and Steve Melvin, and I, 4 of us, each one of us deserves 25% of the credit, but I'm the professor, so I get all the glory, and they end up graduating and getting a good job. The model that I came up with them in 1984 and 1985, we published the first 2 papers that Onur referenced in 1985, and we did it correctly. So we didn't do it the IBM way, which allowed out of order completion, which then meant that they broke the ISA because they couldn't handle precise exceptions. If you go out of order completion, then you've just clobbered the value that was in the register beforehand. So if you do get an exception, you can't back up the machine. In fact, the guys had to get special permission from IBM headquarters in order to release the machine, and they never did another out-of-order machine until years after we did our stuff. So that was probably, as I say, the best idea that I've ever had. And today, just about every machine out there does out-of-order execution. They say, wow, we figured it out and realized what it would take to work. And we came up with mechanisms that worked in most cases. We didn't have a branch predictor yet. We knew we were going to need one, and that came later. But in order to work, not only did you need a branch predictor, but you needed a quick mechanism to recover from a mispredicted branch. And I said that our branch predictor was 97% accurate. What about the other 3%? So if you're 97% accurate and you're going like hell, and then you predict wrong, and it takes you an hour and a half to go down the right path, nobody's going to buy your machine. So you got to be quick. And at the time, the only thing we could think of was this not very good recovery mechanism. And sure enough, we got beaten up. Why does he continue to waste our time reading his papers when he's got this recovery mechanism that is nonsense? Instead of saying, wow, look what he understood and what he led us to be able to work on. And this little piece here didn't work. That's okay. So I would argue that what we need to do as a field is start giving credit if you come up with a deeper understanding that somebody else can then build on and come up with the widget that makes it work. In fact, I would argue that we deserve more credit for the understanding than the mechanism. We finally figured out a mechanism that was fast, and of course, today is just history. But if we don't give credit for the scholarship, which is the understanding, then we're depriving the community from taking the understanding and taking it to the next stage. So research versus scholarship, the rest of the world calls it research when they're just digging at what's been done, trying to understand it. In engineering, we don't call it research until people come up with the widget. You come up with the widget and you go, wow, now we'll publish the paper. No, we should publish the paper based on the understanding. The widget will come later. In fact, a lot less required to come up with the widget than to come up with the understanding. Okay, and that's all the, no credit for the first step if you don't come up with part two. Some dismissed HPS. HPS is the name of the model that we called our work. We told the world it stood for a high performance substrate, which the substrate was the microarchitecture rather than the silicon. And I guess I can tell them the real truth today. It really stands for the first letter of the three last names. I'm P, and I put my two students on either side of me. Wen Mei Hu, that was the H, and Mike Shevenow, that was the S. But some dismissed HPS because of our expensive checkpoint scheme that was there to take care of a mispredicted branch. I would argue that the first step is a more important step. Develop the insights as to what the problem is, publish that to invite others to then carry it to the next step. I value scholarship more. Machine learning. So I am going to pick on some of the, as we were walking over here this morning, one of Professor Mutlu's students said, I'm working on old problems. I won't give away his name, but he said, I'm working on old problems. So I corrected him. I said, no. You're working on real problems. They're old because they haven't been solved yet, as opposed to well, I can't do anything real, so I'll do some pie in the sky. And so I've got a slide on machine learning and another one on something so I actually care about machine learning. In fact, you see one case where we use machine learning to produce value. What's missing? So disasters are just waiting to happen. Some already have. The car that drives into the back of a truck and kills the driver, the woman who was killed on the bicycle. And why does that happen? Because machine learning generalizes from a small set of inputs. So if you look at all the bits that are input to the neural network, we're talking about a huge number of bits, and a bit goes either 0 or 1. So 2 to that power being the number of bits, is a huge number. But the training is based only on a small subset. You might think of it as a large subset. It's like 1 million inputs, but 1 million compared to the input space is still as small. Machine learning generalizes from a relatively small sample, and most people using it have no clue what's really going on. They love it because they get the right answer most of the time. They go, wow, it works. Don't bother me with how it works. I'm just happy that it works and I can publish the paper and get on with it. By the way, it's a powerful tool. In fact, I first worked on machine learning on neural networks. They didn't call it machine learning back then. I worked on neural networks when I was a graduate student. There were 3 groups at the time. The group, Bernie Widrow's group, which I was a part of, Frank Rosenblatt at Cornell, and Karl Steinbuch at Karlsruhe. in Germany. These are the three groups. And how many columns do you have of threshold logic units? One. This was even before backward propagation came along. And we could do a few little silly things with neural networks. The beauty of neural networks, in my view, is if you have a problem, and branch prediction, by the way, is a poster child for machine learning. If you have a problem and you have no idea how to write an algorithm to solve that problem, but you have a lot of data, and you also have the result when you have that data. It's exactly what branch prediction is. When the branch comes in, you have a history of which way the branch went the last so many times. That's the data. And you also know afterwards, after you collect all the information, which way the branch that had that history went. So you've got the history and you've got the answer. Can you come up with a mechanism to predict branches? And the answer is you can't write a program, but you can train a neural network. So how do you train it? The history comes in and it predicts the wrong way. But this is history, so it's from before. So you know the outcome. If the output is wrong, you adjust the weights until the output is right, and then you continue. That's to my way of thinking, that's the beauty of the CNN neural network concept, is that you can't write an algorithm, but you've got the data and you know what the outcome is. Can you now solve the problem? And the answer is yes. So a powerful tool, if we don't have an algorithm, but we have lots of examples and known outcomes. If the branch happened, yesterday, we know which way the branch actually happened. And so we have the outcomes. We can twiddle the neural network and get it right. A powerful tool if we can detect anomalous instances, the woman dying on the bicycle, the guy going through into the truck. So machine learning lets us train. Can we do it dynamically? That is, when we get a mistake, I don't know how many people we have to kill before we get it right. But if we can figure out a way to adjust the training when we see a mistake to include the neighborhood of that instance that gave us the wrong answer, then there's a hope to cut back on the number of bad solutions, and we're off and running. The critical word on that slide is the last word on the slide, dynamically. And I am told that we're now starting finally to look at, are there ways to look at that input space and correct it, because there was no input in the input space that we used that would have predicted the woman dying on the bicycle. Can we fix it so that that doesn't happen? Can we believe the claim? So we publish a paper. In fact, I think you were a co-author of that paper, where we were accused of cooking the books. And we didn't cook the books because we don't cook the books, But there was this guy in the field who didn't like the paper because we didn't reference any of his useless work. And so he sent in a review that said, this paper ignores these great pieces of work, which had nothing to do with the problem. And even any problem it did have to do with was kind of meaningless. Onur was an advanced stage PhD student at the time. He was furious. In fact, if it wasn't for you, I probably wouldn't have pushed this out as I did. And then he says, the guy who wrote in, I don't know that we can trust the results. Think about it. We have these claims of papers, and what do we do with it? What should an author provide to justify those claims? The whole experimental setup? We could do that. You want to publish a paper, you got to publish your entire setup. Or do we simply trust the author to give us his word? I didn't cheat. You know, in the US, we have problems with people now who, I didn't cheat. Some of them don't know the difference between truth and a lie, but that's a digression we won't enter today. Disclosing too much makes life easier for the followers. Is that fair to the person who did the original work? So I do the original work and it takes me 5 years to get the result. And I publish everything that it's got to do that. And then somebody comes along and plugs in a few bits of data and they get a result publishable in a week and a half. Is that a fair situation? Is it fair to the person who first had the idea? But actually, that's the way science works, by people building on what other people have done. And in computer architecture, we just don't do that. Too much computer architecture results are never replicated. You know, in physics, if you do an experiment that replicates a claim that somebody made, you get credit for that. Not in computer architecture, you know? We already know that. Joe Blow did a paper on that. Why are you just repeating his work? That has to change. Will no carrot for replicating somebody else's results? Will we ever be a science until that happens? I'll pick on quantum. I call it quantum when. When? When are we going to have, by the way, we're never going to have a quantum computer. We may someday have a quantum accelerator, which is a specialized piece of stuff that allows you, let me back up to the first accelerator that I know of. It was called the Intel 8087. So if you know the history of the x86 architecture, the first one was called the 8086. And what did it do with floating point? It did nothing with floating point. There weren't enough transistors to do anything with floating point. So what it did is Intel built a second chip. They gave it the name coprocessor back in those days. And what it did was floating point operations. So the 8086 went to memory. So better yet, fetch the instruction, decoded it, go to memory to get the data, et cetera, pass the data off to the 8087. Right? And then the 8087's job was just to do that floating point operation. A baby gorilla in some sense. It's like, I don't know how many of you have fed an infant, you know, you eat, and he's not ready to eat, so he spits out everything. So that's part of the problem, and that's true with the baby gorilla called the 8087, right? So we will have a quantum accelerator someday. That's the magic of the word when. When? When we have enough qubits that we can do something useful with it. And these qubits have to stay stable for more than 3 picoseconds. And the accelerator has to sit in something that operates at better than 0.1 Kelvin. And when all that comes to pass, absolutely. Probably not in our lifetime. When will we be able to do useful work? How many qubits will it take? If you talk to the serious quantum people, they're telling you these advertisements by IBM, et cetera, we now can do 500 qubits. Can't do anything with 500 qubits. The people doing quantum know that. The people doing quantum know it. The people doing quantum will be honest with you, then it's even better. How will a qubit, how long will it have to be stable? What temperature is necessary? What will they be useful for? So right now, and here's one of my predictions. Right now, there's tons of money out there. If you tell a funding agency of a government, doesn't have to be the US, doesn't have to be China. Last summer, I do these annual travels during the summer when I'm not teaching. And last summer, I visited Sweden and Greece and China and the US and Spain. And the governments are pouring money into quantum. So you can be a yo-yo and still get money to work in quantum right now. Why? Because governments are afraid that if they don't, and their adversary does, they're going to break encryption and they're going to be out of luck. And so for self-protection, we better fund quantum. Except the crypto people have realized that, we need to get past this quantum thing. So crypto people don't work in quantum anymore. They work in post-quantum crypto, for which even the quantum people will tell you quantum is not going to be helpful. As soon as the governments get wind of that and really understand it, most of the funding is going to disappear. Not all, because quantum is an interesting paradigm as a theoretical concept to be studied. But it doesn't require hundreds of yo-yos to study it. It requires a few brilliant people. And so what's going to happen, I had this conversation with Papa Demetrio. He said, don't worry, Yale. The good people, the people that are really on top of it, they'll still be funded. But most of the yo-yos won't. And I'm interested in what's going to happen in universities when all of a sudden these people that have been hired like crazy over the last few years, the funding has dried up. Interesting thing to think about. Okay, so where am I on the slide? Even quantum people agree quantum will be useless. Maybe, so now what the quantum people say, well, don't worry about it. We're going to be able to use quantum to be able to simulate a chemical reaction. Wow. And how many governments are going to fund that at the same level that they're funding quantum to protect us from our adversaries on crypto? I don't think so. Still, the hype continues. Funding levels are absurd. Faculty appointments are plentiful. And the reason is everybody's afraid of being left behind. If I come back 3 years from now and there are no quantum people out there, we will not be surprised. The research results require a baseline. That's an interesting thought. So this came out in a faculty meeting that we had for making hiring decisions. And it's interesting. I don't know whether it's true at ETH or not, but we get these faculty candidates, they're fresh PhDs, and they describe what they've done, and they show us the performance, but what they don't do is compare it to anything that went earlier. And so one of my colleagues in microelectronics, he said, I'm not a computer architect, so I have no idea whether this performance is good, bad, or indifferent. Why can't we get these people to tell us how much better they are than what's gone on before? Do research results require a baseline? Supposing I told you, when I was younger, I used to run marathons. Didn't run them really great, but I did always finish. And I got a lot of medals to show for it. In fact, I remember the first time I got a medal for finishing, I gave it to my father. I said, Dad, for you. What's this? It's a medal. I see it's a medal for what? For the New York City Marathon. He said, wow, you won the New York City Marathon. No, Dad, they give you a medal if you finish the New York City Marathon. And he looked at me, and for the first time I realized it wasn't just my mother that was pushing me to achieve. He was also in his own quiet way. And he looked at me with this look on his face. You lost the New York City Marathon? Like he'd created a loser. An anecdote from UT, my school, University of Texas, during our hiring discussion, it wasn't EMAG, it was microelectronics. I screwed up that slide. So if I told you I can run the Marine Corps Marathon, which is an annual event in Washington, D.C., 10 times faster than your grandmother, would you be impressed? Eh? If I told you I could run it half a second faster than the person who won it last year, you would be impressed. But 10 times faster than your grandmother? Not so. So do research results require a baseline? Yes. And that's your challenge. Everybody that is doing research and going to publish, what you need to show is what you come up with, how much better it is than the best thing that's out there today. And if it's not as good as the best thing out there today, why are you wasting our time expecting us to read it? Hardware or software? I love this one. So it used to be that every 10 years I would move from one university to another. And the reason is that I don't hear so good with these things in. I don't hear at all, but that's another problem. After 10 years, I would move on because when they hired me, one of the perks was immediate tenure. But because I can't hear so good, I hear 10 years. And so after 10 years, I left Berkeley, and after 10 years, I left Michigan. I don't know why I'm still at Texas. I think it's a matter of inertia when you start to get old. But my first semester at Berkeley, I taught 2 courses: data structures and computer organization. People used to come up to me and say, wait a minute, data structures is taught by the software faculty. Computer organization is taught by the hardware faculty. Are you a hardware person or a software person? I'm a person. In fact, don't limit your education. If you think that you're going to push software, take some architecture courses, because the software you write is going to be better if you understand the engine that is going to be processing them. And if you're a hardware person, take some software courses, because your hardware is going to be better if you have some clue as to what it's going to be used for. I have a poster child for that, Google's tensor processing unit. You know about that, the tensor processing unit, usually for inference in machine learning. They published a paper with 40 authors, which, I don't know, 40 authors to a paper? Maybe they make you, here, sharpen this pencil for me, I'll make you a co-author. I don't know. But one of the authors was a kid I knew when he was a graduate student at Harvard, Cliff Young. He's incredibly smart. And I learned that the tensor processing unit out of Google had a systolic array, which was one of the good things about that design. You say, wow, a systolic array. I haven't talked about systolic arrays in quite some time. You know, how come? And I looked at the author list and I saw Cliff Young's name there, and I knew Cliff went to Harvard for his PhD, where H.T. Kung went after coming up with the systolic array at Carnegie Mellon, and connect the dots. Cliff took H.T. Kung's course, learned about systolic arrays. He's one of the key guys on the tensor processing unit. He knows about this hardware structure called a systolic array. Plug it in, and it's one of the big pluses of that design. So hardware and software both. Please don't limit your education. You have no idea what you're going to really need to know, 10 years from now. Top down or bottom up. So my thing is that if I'm teaching, I need to be going bottom up. I call it motivated bottom up because I first tell you what we're going to talk about. Motivate. I'm not teaching, I'm motivating. And then I get in there and teach. And what I teach is based on what you already know. So you can build on what you know until I get to here. Then I motivate, and then I teach. Motivated bottom up. Bottom up is the right answer if what you're doing is trying to make people understand. Because they understand everything below what you're teaching them, you can use that to build that next thing. Top down is what you do if you're designing a new structure. You don't want to do a new structure bottom up. You'll end up with the old structure with a pimple on it. You want to start with a clean sheet of paper. But now you know the underpinnings. You're not being taught the underpinnings. So you have the free hand at going top down. If you try to do top down, too many classes do that. Critical mistake in my view. Because if you're learning top down, you're continually memorizing what the hell's going on because you don't have any anchor. So bottom up for understanding, top down for designing. You know, why does a football team spend a lot of time doing exercises before they get into a scrimmage? Why do people studying karate? First, you do the katas before you get into a bout. Music. Pianists do the etudes before they do Beethoven or whoever your favorite composer is. So you build from the bottom, understand what you're doing, and then you move, you keep going. Not us. Too many courses go top down, requiring memorizing until you finally hit the bottom. I think that's a mistake. So top down or bottom up. Unfortunately, the last bullet is the most recent problem I have. Used to be that I would argue with people, do you go top down or do you go bottom up? And I explain bottom up is the right answer. Today, that argument doesn't even hold anymore. Most people, it seems, when they want to do top up, they don't have any time to waste on compilers or architecture or operating system, any of that stuff, you know? Just move on. So I did include a little bit about the freshman course. The correct first course, and there I say ECA majors, I really mean all engineering students, is the motivated bottom-up approach, build on what students know, which memorizes the requirement for memorization. If they already know this, they don't have to memorize it. Now you can build on it. And so they internalize rather than memorizing, which makes all the difference in the world. In fact, students who do it this way can debug their own programs. They don't have to go to the TA. I gave a lecture on education, and I said, you know what these kids do? They create this mess. They take it to the TA. The TA goes, oh my God, does the first half of the problem. Says, okay, now you finish it. What does the kid do? Goes to another TA. Graduates without ever having written the program on his own. So motivated bottom up, build on what students already know, memorization, start with the transistor, then gates, then muxes and decoders, then memory, finite state machine, and now you got a computer. And now they know what a computer is all about. They can write programs for it and debug their programs by themselves. Students understand how the computer processes their programs, better able to debug their own programs. Not the case for students taking programming in high-level language X. And there are, you know, how many high-level languages are there out there? 2,000? Actually, you may be surprised, but that's about the right number. That there are about 2,000 high-level languages somewhere on the planet where people are actively engaged in writing, debugging, modifying code for. If I mentioned that COBOL is one of the most prolific high-level languages, you know, maybe some of you like me, you don't have a clue with what's in COBOL, but there are people doing useful work. Okay, programming after they know how the computer works. And the EC curriculum, each relevant course later on is going to deal with some aspect of the computer. So the correct first course, which is what we do at about, I don't know, we've got 400 adoptions, and we've got about 5,000 that are still doing it incorrectly, in my view. I said that there. About four, but except I used the more correct. I didn't say incorrectly, I said wrong, which is true. Freshman course, I started at Michigan We called it ECS 100, which is where I met. I actually didn't meet Onur. That's where Onur met me, because he was a freshman at Michigan, and there were 400 of you in the class. So I didn't know you until later on. Luckily, I met you so that I could be your student now for the next 20 or 30 years. Choose a computer model that is simple, the LC33, LC for little computer, 3 because I got it wrong. I thought I'd fixed it, I hadn't. Now I'm pretty happy with the correct model. Continually build on what they know, raising the level of abstraction, memorizing as little as absolutely necessary, trying very hard not to introduce magic. You know, if you do it the high-level language and the kid doesn't know the difference between having the value 4 in location 6 and having the value 6 in location 4, forget it. You're never going to succeed. So there's a picture of memory. It's not 4 gigabytes, it's 4 trits. So each row represents a word of memory, and the fact that there are 3 gated latches there represent 3 bits that make up that word. And so if you look at the left, where you see in the top left, A sub 10, that's the address. 4 locations of memory, you need 2 bits of address. And what you see down that left column is a decoder, which is telling you which of the 4 words you're accessing. And if you're storing, then you need the right enable bit. If you're reading, you don't need the right enable bit. You need to pick off the output of the corresponding bit lines to give you the results. And the students understand that after the second week of the semester. Here's the instruction set. Only 15 opcodes. The high 4, 16-bit instruction, high 4 bits is the opcode, which give you 2 to the 4, which is not really 15, it's 16. Except one of the kids in the class, 400 students, kid raises his hand. Why do you have a return instruction as one of your opcodes? Isn't that just a special case of the jump instruction? I said, wow. So we got rid of the return instruction, and I left it as a reserved instruction. Anybody wants to augment the instruction set. And so the LC3, 15 opcodes. And every few years he writes to me because he needs a letter of recommendation. And he reminds me that he was the student that got rid of the return instruction. But this is powerful. There's only one arithmetic, add. You want to subtract? Well, you can form the negative. You want to do A minus B? Form the negative of B and then do the add. One opcode, add, for arithmetic. For relationals, for logic too, and not. And that's good enough. You say, well, why didn't you use NAND? I could have, except that NAND is kind of counterintuitive, and the not makes sense. You want to multiply? Add. You want to divide? Subtract. So don't waste a lot of opcode space on arithmetics and logicals. Conditional branch done on a condition codes, a P bit, a Z bit, and an N bit. But you know it has to be one of the 3, so it's not N and it's not Z, it must be P. Why did you waste a 3rd condition code? Because having that duality allows me to not have to turn the code into spaghetti code in order to accommodate the condition codes. So I've got a conditional branch, and I've got 3 loads and 3 stores with 3 different addressing modes: PC relative, register plus offset, and indirect. Indirect. Why do you have indirect? Nobody builds machines with indirect these days. That's right. Except indirect says, I want to do a load. This will tell me where to go to find the address of the location of which I want to grab the data and put it into this register. Wow. What do we call this operand that's telling us where to go to find the address of the data that I'm going to write into the register. We call it a pointer variable. And kids have pointer variable trouble from day one. So what I decided to do is have load indirect and store indirect. The problem with pointer variables goes away. By the way, I have an advanced version of the LC3, which they take as seniors, and I removed LD, load indirect and store indirect, from the senior ISA. Why? Because if they're still having trouble with pointers when they get to be seniors, they probably shouldn't be majoring in EE, maybe history or mechanical engineering. Here's a picture of the state machine for the LC3. Here's a picture of the data path for the LC3. They can master all this before they start writing programs, and then the programs become terrific. It's actually good for all engineering students, but I'm not cognizant of the clock, so I will not deal with non-EEs. How much better branch prediction accuracy? Why does much better branch prediction accuracy not translate into better IPC? And I wish I could get the reviewers to understand this. Most obstacles have more than one cause. And if you come up with something that fixes a cause, you don't see performance because there are still other obstacles. It's only when you get the last one that you actually see the big jump in performance. So I get the review back saying, yeah, you got this great prediction accuracy, but you don't show any IPC benefit. Most bottlenecks are due to multiple causes. Fixing one cause may yield no visible improvement when the last cause is fixed. Bingo. And I keep hoping that I'll get reviewers that get it. Be generous in giving credit. Yeah, you know, I get tired of people that think that they are, you know, the world's greatest. Look what I did. Nobody's as good as me. I have two examples from my own history, branch prediction and helper threads. I invented both of them, but I wasn't the only one. So Kimming So and his colleagues at IBM came up with my branch predictor. But they probably, they may even come up with it before I did. I don't know. I teach at a university. I can publish before I even know what the hell I'm doing. Kimming So works for a company. He has to get a release from legal before he's allowed to publish it. So maybe he did come up with it before me. I don't know. But I published it in Micro in 1991. He published it in ASPOS in 1992. So I get the credit. He doesn't. When I teach our branch predictor, I always tell them Kimming So. In fact, I would have hated to be just think, you know, you're sitting there in the office and you pick up the proceedings and you see your branch predictor in the proceedings. And what do? He's a good guy. He credited our work in his submission to ASPOS. And the good news is ASPOS let him do it. Helper threads. I came up with that one also. So did Michel Dubois at USC. I published it in ISCA. Everybody reads. He published it as an internal USC technical report, which nobody reads, both at the same time. Give credit to other people's work. So what do I say? If you think you're the only smart person, go take a nap. You know, it never hurts to give credit to other people's work. Heterogeneity is the answer. Absolutely. What was the question? Performance. That's always the answer. And heterogeneity means you're designing something for a purpose that you have in mind. And if you're doing it for a purpose you have in mind, then you better be getting performance by so doing. So that's what heterogeneity is all about. For performance purposes, you're designing this thing to do a good job on that problem. May be useless on any other problem. I work on my own car. If I want to undo the 1-inch bolt, the 1/2-inch wrench doesn't do me any good. I have a set of wrenches, heterogeneity, each wrench for a bolt. Of course, I could replace that with a single monkey wrench, adjustable wrench, except if the bolt is on there tight, for those of you that had experience with this, that monkey wrench really doesn't do the job. So the hetero result is the right answer. Why did it take so long? My first example with hetero was the writable control store of the PDP 1160. PDP 11 came out in 1970, and the Model 60, they gave you some writable control store and an instruction in the ISA, which was an entry point. It was called EMT, Emulator Trap, an instruction in the ISA to point you to the microcode. And then you could write whatever microcode you wanted to optimize the tasks that you had at hand. Turn that data path into hetero. And that's where I cut my teeth on hetero. I was doing a lot of consulting for DEC at the time, and I discovered that for VAX, VAX was pretty much the ISA of the 1980s. x86, 1990s, IBM 360, probably 1970s. And I discovered that these two instructions, here's two instructions, add ABC and add ACB. And I'm using the format that most machines do now, which is ABC, destination, source. It's not the way it was back then, but most of you don't remember back then, so I'm using the current terminology, which is the destination is A. The two sources, B and C, or C and B. Now, what's the difference in doing that? It turns out, maybe you don't know this, the add operation is what we call commutative. A plus B, B plus A, no difference. I discovered that depending on the addressing modes that the compiler put the instruction in, it was better to do one rather than the other. You get a good performance benefit by using one of those two rather than the other one. And I went to the guy I was consulting for, and I said, hey, I've got a way to improve the performance of VAXs running to improve the performance of problems running on VAXs if we make this one change to the compiler to get the addressing modes to accommodate this little thing that I discovered. And the answer is no. Now what you're going to do is make this VAX different from all other VAXs. And we insist that the code generated by the compiler is going to work the same for every implementation. Let's not screw around with hetero. I was on a panel at High Peak in Pisa in 2010. And again, the Lone Ranger, because we were discussing multi-core chips, and I'm arguing for hetero, for different functions. No company will ever do hetero. You need different design teams to do the different cores. You do one design team, step the reticle, and now you have different cores. So I insisted hetero, everybody else insisted homogeneous, make all the cores the same. I don't know how many of you follow the American game of football. Each team has 11 players on the field at one time. How many quarterbacks? In an American game of football, each player is designed specifically for what the job is required. An inner lineman has to be big and strong. A wide receiver has to be fast. A quarterback has to be able to throw. Hetero, each player designed for the purpose. 11 players on the field. How many quarterbacks? Well, you could have 11 quarterbacks, homogeneous design, you probably would never win a game. What took the rest of the world so long to catch on? In 2012, we designed Morph Core, which was a functional unit that could be morphed, changed, depending on the nature of the code that it needed to execute. You needed one heavyweight because you were doing Amdahl's law, or maybe you're going through a critical section. You design this, you fix this thing with past transistors that you can break the connection or not into one heavyweight. Or if you're doing TLP, thread level parallelism, you don't need a heavyweight, but you need lots of things to handle the throughput. Different collection of past transistors, and you go like hell. Or NLP, no level parallelism. Then you just disable everything except one of the Mickey Mouse and save energy while things are going on. The GPU, what I need is 10,000 threads because I want to work on 10,000 pixels. How can I do that? Well, if you understand SMT, if you understand SIMD, and if you understand predication, you can put those all together into this hetero design to be able to get 10,000 threads all running. Pentium issue with, it's kind of interesting. Pentium, 1992, 2 pipelines. Pentium Pro, the next design, like 4 or 5 years later, 3 pipelines. So how about if you let the compiler know whether they're compiling for Pentium or they're compiling for Pentium Pro? And you need separate compilers to do that. And Intel actually did that. If you use the Pentium Pro compiler on Pentium, disaster. Use the Pentium compiler on Pentium Pro, disaster. But use the right one, performance win. I've already told you about the historic array. Branch prediction. So the best branch predictor out there is Tage. That's Andrei Sesnet. And it requires, like my original version of the 2-level predictor, which his is also a 2-level predictor, is it requires an explicit, unique history state. And if you don't have a unique history state, because some things may come a little bit early, a little bit late from the history, then Tage fails. And the reason it's only 98% prediction accuracy is because of that perturbation, if you will. But what's good about neural networks is it handles the perturbations just fine. It's all about clustering the neighborhood. So if you build a neural network engine based on the perturbation, you will do well on exactly those branches that Tage fails on. So we invented that. We call it BranchNet. We published it in Micro a few years ago. What is it saying? It's saying that if you have one neural network, you could do fine. But if you have 2 and they're different, then you get a win. So branch prediction is better than Tage because we've added this second way of allowing the history to be perturbed.
Yale.
Yeah, I'm out of time. I can finish up in about 5 minutes. So that'll kill 5 minutes off their coffee drink. So what do I want to do? You going to give me 5 minutes?
Okay. Yeah.
Okay. Where we are today, Dennard scaling is gone. Moore's law is almost gone, although maybe it isn't. What Moore's law is, I won't tell you. I'll assume you know. It's about to end, and down at the bottom it says, but they may be wrong. Meanwhile, they've given you all this stuff over the years, and I'm going to skip it. What if Moore's law does end? No more faster transistors. The smaller the transistor, the faster it can switch, which means the higher the frequency you can operate on. So no more increase in transistors. We won't even be able to have them all powered on at the same time. So how do we stay on the performance curve? This slide I came up with 40 years ago to show that problems are really solved by the electrons, but since we can't speak electron, we can't get the thing in one global optimum. We have to go through these several layers. And what came out very shortly thereafter was a white paper of MIT saying there's plenty of room at the top. Moore's law may have ended, but we can still do things at the algorithm layer, at the programming layer, at the compiler layer. And I say there's still plenty of room at the bottom, since I've got 50 billion transistors and I'm not taking advantage of it yet. And so here's a slide with MIT at the top and me at the bottom. Everybody seems to be accelerator happy today. An accelerator is all about heterogeneous for performance, which means if I do enough of these things, I'm going to have to worry about communication, and I need to control that communication and the output of these accelerators. So like a symphony has all these musicians, they don't get to produce a symphony until the conductor comes out and gets them working together. The conductor of a symphony is like a simple von Neumann machine controlling over the communication paths, each of these heteros. And of course, they added features. And when you add a feature, do you add it to the ISA? Do you add it to the microarchitecture? Here's some examples. If you add something to the microarchitecture and you decide later on it was a bad idea, you stop adding it. If you add something to the ISA, you're probably stuck with it forever. And we've had our collection of silliness, delayed branches, for example, register windows, for example. What next for hetero? Chiplets to allow the substrate to also be part of the wherewithal that we're improving performance. You know, in the old days, when we first started with MOSFETs, we only had one type, N-type transistors. We had P-type, but we couldn't get N-type and P-type on the same substrate at the same time. So what we did instead of P-types was we had a pull-up resistor, which consumed energy, until finally we figured out how to get the P-type on the same substrate and get rid of that loss of energy by the current that the resistor would draw. So chiplets are going to help in the same way. It's going to allow us to add the substrate to the accelerator that they're building. And most importantly to me is expose the microarchitecture of the compiler. Better performance. Someday cure cancer, predict tsunamis. And the pushback is this will destroy portability. No company is going to be willing to destroy portability. I get enormous pushback. Without portability, the economics isn't there, industry won't buy it. My response, economics be damned. There's more things, the things more important than economics. Things that shouldn't have a price tag, things that need much greater performance, and hetero means much greater performance. We already have existence groups. What else if we can reject a... So on portability be damned if we get performance by breaking the layers and make some important headway on some very important problems. I think it's worth pursuing. In short, don't be afraid to exploit the microarchitecture to solve important problems. Be careful about adding features to the ISA. They'll be with you for a very long time. And don't be a top-up person. Understand the underlying structures so you can exploit them effectively. And I promise you a picture of the microarchitecture. Onur's going to kill me if I go much longer. I'll leave you with at least the slide. Notice I start off with chiplets. but we're running out of time. And finally, for this week, I will make a couple of comments that'll say, hey, look, he's coming. He's got a, you know, those things that they use in vaudeville. He's going to hit me with one of them. This is my last slide, except for my thank you slide. So you've got 4 of these things coming up the rest of the week from brilliant researchers. Your job to pick their brains. If you did not understand something, they said, ask, and they'll explain. They have a tough job ahead because they really want to give you at least 18 lectures, but they only got 9 to do with it. And so they're going to, I hope they resist it, but I've had a lot of experience where they will cram too much stuff. Your job, slow them down. They said something you didn't understand, make them explain it. The best thing you can get from them is not lots of stuff. You can read lots of stuff. The best thing you get from them is the insights they've got because of the time they've invested in the last several years. To get that, you will need to ask questions. Don't be shy. At lunch, at coffee breaks, wherever, whenever you get a chance. Obrigado. Sorry,
That's okay. I can tell you're confused where you are.
where I am, where.
Based on the language you're using.
Oh, obrigado?
Yeah.
No, so I've done this now. Every PowerPoint lecture, put thank you in a different language. Merci, danke,
I know.
obrigado. And it cracks them up. And then when you get to some of these Central Asia countries, where nobody, you can like, and they would not go. But I like those.
Do we have time for questions on there, or
No, you get the questions in the coffee.
maybe the coffee break? Maybe is there a really burning question that anybody wants to ask you? Or okay, there's one burning question. I'll take that one and nothing else. I have a question.
This is the compiler box between your MIT and your.
Yeah, you know, so I've been struggling with this. So the compiler. So one of the things I was thinking of is, so the way I get around that is I say the language. You know? If you're programming an assembly language, certainly use an assembler, but there's not a lot of stuff you really do with the assembler. In fact, I would argue with the operating system, with the math library. And what I wanted, so by the way, when I came up with this slide, it was like over 40 years ago. And I wanted it for a different purpose. Today, in fact, the best rendition of that slide today is done by Patt. He takes the thing and he drives a lightning bolt through the whole thing, saying, you really have to be aware of everything. And he's right. When I came up with the slide, you didn't have to be aware of everything. You had to know the layer you were doing. It'd be good if you knew the layer below, because it's producing the raw material. And it's good to know the layer above, because that's what you're building your layer for. But that's all you needed to know. And I argued with myself a lot on some of the math library, the operating system, the compiler. Not to, of course, you're absolutely right.
Okay.
But I did mention the compiler with respect to the portability thing.
For Yale, you'll be around for the week.
I'll be around the whole week,
break.
yeah.
Whatever is left of the coffee break. Andrea, do you have an announcement?
We'll just go back to the registration desk, and then we can adjust some copy there. Thanks,
Okay.
again.
Thank you.
Yeah, you know.